started section second. We have com- we have completed chapter 8, chapter number 8. Then let us start a 7th chapter, implementation of OMT, object modeling technique. So in this chapter we will study use of programming language and database system, object oriented style, features of object oriented languages, applications of OMT like object diagram compiler, computer animation, case study of hotel management system, course management system. For this chapter, we require a textbook, Object Oriented Modeling and Design by Rambagh of Tata McGrath Hill publication. And for this chapter, a CO course outcome is devise the real world problem using object oriented modeling technique. So before starting the syllabus point, we go to the introduction of implementation of OMT. So writing code is an extension of design process. Whenever you start any project or any program, so writing code is extension of the design process. Writing code should be straightforward, almost mechanical, that is go in one direction, not in backward direction, because all the difficult decisions should already have been made during design. After design, then you should have translation into the practical application. After practical application, then peculiarities of the particular language. Decisions have to be made while writing code, but each one should affect only a small part of program, so they can be changed easily. Nevertheless, the program code is the ultimate embod- embodiment of the solution of to the program. So the way in which it is written is important for maintainability and extensibility. So implementation using programming language. Most executable languages are capable of expressing the three aspects of software solution: data structure, dynamic flow of control, and functional transformation, that is object model, dynamic model, and functional model. So data structure is expressed in declarative, that is non-procedural. It is a subset of language. The statements that are used to declare data structures are sometimes mixed in with the procedural statements but are not executable. In some languages such as Ada, it is a language. Ada, a sharp distinction is made between external specification, which is purely declarative, and internal specification, which is often combined with procedural statements. Flow control may be expressed either procedurally, that is conditional, loops, or calls. In conditional, that is if, switch, then loops for while, do while, then for calls, that is functional of call by function, call by reference. Then non-procedural languages contains the parts rules, constraints, tables, statements, that is polymorphism, encapsulation, inheritance, etc. So traditional languages are purely procedural, although the programmer can implement non-procedural constructs as data. Non-procedural languages such as rule-based systems, constraints, maintain maintenance system, and logic programming languages support entirely different ways of organizing programs. Their relationships to the object oriented concepts is still under exploration. So support for concurrent threads of control is lacking in most major languages except Ada. Multitasking, inter-process communication are provided by the modern operating system but must be accessed from the programs using accord subroutine calls. Concurrency can also be stimulated within programs using coroutines, control models, or event handlers. Functional transformations are expressed in terms of the primitive operators of the language as well as calls to the subprograms. Most procedural languages are similar in the kinds of functionality they support and do not differ greatly from the Fortran. Fortran is language. Lisp also is language. Lisp permits the construction of functions at runtime, which permits interesting and confusing operations. So implementation of object-oriented design is easiest using object-oriented language, but even object-oriented languages vary in their degree of support for object-oriented concepts. Each language represents a compromise among conceptual power, efficiency, and compatibility with the previous work. Even when a non-object oriented language must be used, an object oriented design is beneficial. Object oriented concepts can be mapped into non-object oriented languages or eventually converted to machine language. Anyway, as much as an issue of expressiveness, use of non-object oriented language requires greater care and discipline to preserve the object-oriented structure of the program, and programmer cannot obtain help from the language in finding violations. Any language, object-oriented or non-object-oriented, as a tool that can be used well or poorly. Object-oriented programming can greatly improve the expressiveness of programs, but it can also increase the opportunity for obfuscation by careless programmers. As with any craft, good programming As with any craft, good programming requires discipline. As with any craft, good programming requires discipline and adherence to principles of good style. Then second point, implementation using a database system. When the main concern is access to persistent data rather than operations on the data, a database is often the appropriate form of implementation. The main focus of a database is a structure and constraints on the data. The database commands typically operate on the sets of data from the database, incorporating a high degree of parallelism. While most conventional languages are highly serial, database operations are much less procedural than conventional programming language statements. Although they are more procedural than a rule-based system, database provides concurrent operations on the data by different users as a part of their fundamental structure. Most RDBMS relational database management system provides separate languages for data declarations and operations, analogous, analogous to the distinctions in programming languages. The data definition language is used to declare structure of data. A query language may be provided which allows the expression of functional transformations, record locking and update, and flow of control. The query language may be limited to simple record access based on fields that acts as keys, or it might offer more of the features of a general purpose programming language. Some recent object-oriented database systems attempt to integrate an object-oriented language with a database in a single seamless package. Operations may be defined for each class of object, but the programmer need not explicitly read and write information to persistent storage. Although object-oriented database systems promise better performance and easier use in long run, they are not yet as mature as conventional RDBMS and may also pose problems integrating with existing conventional applications. Then object-oriented style. So good programmers do more than simply satisfy their functional requirements. Programmers that follow proper design guidelines are more likely to be correct, reusable, extensible, and quickly debugged. Most style guidelines that are intended for conventional programs also apply to object-oriented programs. In addition, facilities such as inheritance are peculiar to object-oriented languages and require new guidelines. We represent object-oriented style guidelines under the following categories. Although many guidelines contribute to more than one category. So first, reusability, second, extensibility, third, robustness, fourth, programming in the large. So we'll see in detail one by one. So first is a reusability. So reusable software reduces design, coding, and testing cost by amortizing effort over several designs. Reducing the amount of code also simplifies understanding, which increases the likelihood that code is correct. Reuse is possible in conventional languages, but object-oriented languages greatly enhance the possibility of code reuse. So, reusability have three parts: kinds of reusability, style rules for reusability, and third is using inheritance. So, we will see one by one in detail. So, first is kinds of reusability. There are two types of reuse: sharing a newly written code within a project. This is first. And second, a reuse of previously written code on a new project. So similar guidelines apply to both types of reuse. Sharing of code within a project is a matter of discovering redundant code sequences in the design and using programming language facilities such as procedures or methods to share their implementation. This kind of code sharing almost always pays off immediately by producing smaller programs, faster debugging, and faster iteration of the design. Planning for future reuse takes more foresight and represents an investment. It is unlikely that a class in isolation will be used for multiple projects. Programmers are more likely to reuse carefully thought out subsystems such as abstract data types, graphics packages, and numerical analysis libraries. Second, style rules for reusability. So there are four parts: keep method coherent, keep methods small, keep methods consistent, and maintain parallel structure when possible. So keep method coherent. A method is coherent if it performs a single function or group of closely related functions. If it does two or more unrelated things, break it apart into smaller methods. Then keep methods small. If a method is large, break it into smaller methods. A method that exceeds one or two packages is probably too large. So by breaking a method into smaller parts, you may be able to reuse some parts even when the entire method is not reusable. Then third, keep methods consistent. Similar methods should use the same names, conditions, argument, order data types, return value, and error conditions. Maintain parallel structure when possible. The Unix operating system offers many examples of inconsistent functions. For example, in the C library, there are two inconsistent functions, two output string, puts and fputs. So put functions writes a string to the standard output followed by a new line character. F writes a string to a specified file without a new line character. So avoid this kind of inconsistency. Separate policy implementation. So policy methods make decisions, shuffle arguments, and greater global context. Possible methods switch control among implementation methods. Policy methods should check for status and errors. They should not directly perform calculations or implement complex algorithms. Policy methods are often highly application dependent, but they are simple to write and easy to understand. Policy methods are the mortar. Implementation methods perform specific detailed operations without deciding whether or why to do them. If implementation methods can encounter errors, they should only return status, not take action. Implementation methods perform specific computation on fully specified arguments and often contain complicated algorithms. Implementation methods do not access global context, make decisions, contain defaults, or switch how to control. Because implementation methods are self-contained algorithms, they are likely to be meaningful and reusable in the context. Implementation methods are the bricks. So do not combine policy and implementation in a single method. Isolate the core of the algorithm into distinct, fully specified implementation method. These require abstracting out the particular parameters of the policy method as arguments in a call to the implementation method. For example, a method to, to scale a window by a factor of 2 is policy method. It should set the target scale factor for the window and call on the implementation method that scales the window by the arbitrary scale factor. Later, you decide to change default scale factor to another value such as 1.5. So you just have to modify the parameter in the policy method without changing the implementation method, which actually does not the work. Then provide uniform coverage. If the conditions can occur in various combinations, write methods for all combinations, not just the ones that you currently need. For example, if you write a method to get the last element of the list and write one to get the first element, then broaden the method as much as possible. That is to generalize, try to generalize the argument types, preconditions, and constraints, assumptions about how the method works, and the context in which the method operates. Take a meaningful action on empty values, extreme values, and out of bound values. Often a method can be made more general with a slight increase in a code. Avoid global information, minimize external references. Referring to a global object imposes required context on the use of a method. Often the information can be passed as an argument, otherwise store global information as part of target object so that other methods can access it uniformly. Then avoid modes. Functions that are drastically change behavior depending on current context are hard to reuse. Try to replace them with modeless function. For example, a text processing application requires insert and replace operation. One approach is to set a mode to insert or replace, then use a write operation to insert or replace text depending on the current mode. A modeless approach uses two operations, insert and replace, that do the same operations without a mode setting. The danger of modes is that an object left in a mode in one part of the application can affect the operation applied later in the application. Then third is using inheritance. The preceding guidelines improve the chance of inheriting shared code. Sometimes, however, methods on different classes are similar but not similar enough to represent a single inherited method. There are several techniques of breaking up methods to inherit some code. Then subroutines. The simplest approach is to factor out that the common code into single method that is called by each method, and the common method can be assigned to ancestor class, that is previous class, and this is effectively a subroutine call and action in figure. See in this figure there are two methods, method A, method B, but they are they have common parts, so they are accessed by common method. Then next, factoring. In some cases, the best way to increase code reuse between similar classes is to factor out the differences between the methods and different classes, leaving the remainder of the code as a shared method. This approach is effective when the differences between methods are small and similarities are great. So as shown in figure 2, common partitions, suppose this is the method A, this is the method B. So the common method, the common code, call operation M, common code. So there are method A, method B. So method A access the common method, common code or common operation. Similarly, method B also access the common method, common code or common operations. So the new method calls an operation that is implemented by different method containing code differences in each subclass. Sometimes an abstract class must be added to hold the top level method. This approach makes it easier to add new subclasses because only the difference code need not be written. Then a package for plotting numerical. Here we are taking one example. So for plotting numerical data provides good illustration of factoring such as data graph. This data graph is abstract class that organizes a common data and operations for its subclasses. So one of the data graphs method is a draw. Suppose we want to graph and there is operation is a draw. So which steps are required? So first step is a draw border. So for drawing border there is a some scale data, then draw axis, x-axis, y-axis, z-axis. So then plot that data, then that drawing have some title, that is a draw title, and a draw legend. So subclasses of data graph. Suppose I want to draw graph data or data graph. It has subclasses such as line graph, bar graph, scatter graph, draw borders, titles, legends the same way but differ in the way they scale data, draw axis, or plot data. Each subclass inherits method, draw border, draw title, and draw legend from the abstract class data, data graph, but each subclass defines its own method for scale data, draw axis, and plot data. The method draw need only be defined once on the class data inherited by each subclass. Each time the draw method is invoked, it applies draw border, draw title, and draw legend inherited from the superclass and scale data, draw axis, and plot data supplied by the subclasses for the object. To add a new subclass, only the three specialized methods need to be the written. First method is delegation. Sometimes it appears that use of inheritance would increase code reuse within a program when a true superclass or subclass relationship does not exist. Do not give in to the template inheritance. Use delegation instead. Inheritance should only be used when generalization relationship is semantically valid. Inheritance means each instance of subclass truly is instance of superclass. Thus, all operations and attributes of the superclass must uniformly apply to the subclass. Improper use of inheritance leads to programmer that hard to maintain and extend. Object-oriented languages are permissive in their use of inheritance and will not enforce the good programming practice that we recommend. Delegation provides the proper mechanism to achieve the desired code reuse. Operations in code is caught in the desired class and forwarded to the another class for actual execution. Since each operation must be explicitly forwarded, unexpected side effects are less likely to occur. The names of operations in the catching class may differ from in those in the class supplying the operations. Each class should select names which are most appropriate for its purposes. Second is encapsulate external code. Often you will want to reuse code that may have been developed for an application with different interfacing conventions. Rather than inserting a direct call to the external code, it is safer to encapsulate its behavior within an operation or a class. This way, the external routine or package can be changed or replaced, and you will only have to change your code in one place. For example, you may have numerical analysis application, but knowing that reliable matrix inversion software already exists and you don't want to re-implement the algorithm in your object-oriented languages. The matrix class might be written to encapsulate the functionality provided by external subroutine package. The matrix class would have, for example, an inverse operation that takes the tolerance for singularity as an argument and returns a new matrix that is the inverse of the operation's target. Then most software extended in the way that its original developers may not expect. The guidelines for reusability enhance extensibility as well. In addition, the following object-oriented principles enhance the extensibility. First is encapsulate classes. Second is hide data structures. So in encapsulate classes, a class is encapsulated if its internal structure is hidden from other classes. Only methods on the class should access its implementations. Many compilers are smart enough to optimize operations into direct access to the implementation, but the programmer should not respect the information in other classes by never reaching inside the class for data. Hide data structures. So do not export a data structure from a method. Internal data structures are specific to a method's algorithm. If you export them, you limit flexibility to change the algorithm later. Then third, avoid traversing multiple links or method. A method should have limited knowledge of object model. A method must be able to traverse link to obtain its neighbors. and must be able to call operations on them, but it should not traverse a second link from the neighbor to a third class because second link is not directly visible to it. Instead, call a operation on neighbor object to traverse the operation. If the association network changes, the operation method can be rewritten without changing the call. Similarly, avoid applying a second operation to the result of an operation call unless the class of result is already known as an attribute, argument, or neighbor, or the result class to perform combined operation itself. The principles in this paragraph proposed by proposed in the paper which is published in 1989 and it is known as law of Demeter. So avoid use use method instead. Avoid case statements on object type. Use methods instead. Case arguments can be user one test. Internal attributes of an object must but should not be used to select behavior based on object type. Dispatching operations based on object type is the whole point of methods, so do not circumvent them. Distinguish public and private operations. Public operations are visible and outside a class and have published interfaces. Once a public operation is used by other classes, it is costly to change its interface. So public operations should be carefully defined. Private operations are internal and in the class and are used to help implement the public operations. Private operations can be deleted or their interfaces can be changed to modify implementation of the class with impact limited to other methods on the class. So why classify operations as public and private? There is no need to bother the user of class with internal details. Private methods just confuse the external user of class. Since private methods depends on internal implementation decisions, the method designer may change the number and types of arguments if the implementation changes. Private methods may rely on preconditions or state information created by other methods in the class. Applied out of context, a private operation may calculate incorrect results or cause the object fail. Private methods add modularity. Internal details of the method only affect the methods on the class, not other methods. Similarity, Similarly, attributes and associations should be classified as public or private. In addition, public attributes and association may be classified as read-only or writable outside the owner class. So you should strive for efficiency in writing methods, but not at the expensive robustness. A method is robust if it is not fail even if it receives improper parameters. Robustness against internal bugs may be trade-off against efficiency. Robustness against user errors should never be sacrificed. Protect against errors. Software should protect itself against incorrect user input, should never cause a crash. Any method that accepts user input must validate input that could cause trouble. Method designer must consider two kinds of error conditions. Application, that is user errors, are identified during analysis and report conditions that exist in the problem domain. For example, an automatic trailer machine, that is ATM, application should report or process errors about ATM card scanner and communications lines. The response to these errors is part of analysis. On the other hand, low-level system errors concern programming aspects of a method. These low-level errors include operating system errors such as memory allocation errors or file input-output errors and handwritten hardware faults. Your program should check for these errors and at least try to die gracefully if nothing else is possible. Try to guard against programming bugs as well as possible to give good diagnostic information even if fatal bugs occur. During development, it is often worthwhile to insert internal assertion into the code to uncover bugs, even though the checks will be removed for efficiency in the production version. A strongly typed object-oriented language provides greater protection against type mismatches, but assertion can be manually inserted in any language. Then optimize after program runs. Don't optimize a program until you get it working. Often programmers spend too much effort trying to improve portions of code that are infrequently executed. Measure the performance within the program before optimizing it. You may be surprised to find that most parts consume little of the total time. Study your application to learn what measures are important, such as worst case times and operations frequencies. So, if an operation may be implemented in more than one way, access the trade-offs of the alternatives as they relate to memory, speed, or simplicity of the implementation. In general, avoid optimizing of the program, then you have to optimization compromises extensibility, reusability, and understandability. If the methods are properly encapsulated, they can be replaced with optimized versions without affecting the rest of program. Then validate arguments. External operations, those available to users of the class, must rigorously check their arguments to prevent failure, but internal methods may assume their arguments are valid for efficiency reason. Public methods must take more care to check the validity of arguments because external users are more likely to violate restrictions on arguments. Internal or private methods can often assume preconditions since the implementer has tighter control and can rely on the public methods that call them for error checking. Don't include arguments that cannot be validated. For example, the infamous scanf function in Unix reads the line of input into internal buffer without checking size of the buffer. This loophole has been exploited to write virus programs that force a buffer overflow in system software and did not validate its argument. So don't write or use operations whose arguments cannot be validated. So avoid predefined limits when possible. Use of dynamic memory allocation to create data structures that do not have predefined limits. During design, it is difficult to predict the maximum capacity ex- expected of data structures in an application, so do not set any limits. The fixed limits on symbol table entries, use names, file names, compiler entries, and other things should be long over. Most object-oriented languages have excellent dynamic memory allocation facilities. Instrument the program for debugging and performance monitoring, just as hardware circuit designer instruments an IC board. with test points. You should instrument your code for the debugging, statistics, and performance. The level of debugging that you must build into your code for debugging, statistics, and performance. The level of debugging that you must build into your debugging that you must build into your code depends on the programming environment presented by the language. In Smalltalk is a language. In Smalltalk, for example, a class browser allows a developer to explore the class hierarchy, displaying attributes and code for methods. An inspector lets the use interrupts executions and print the internal state of instance. If your implementation language does not have similar capabilities, then you can provide print methods for each class. So these methods can be accessed from also you can add debug statement to the methods. These debug statements are conditionally executed depending on an instance variable that contains the debug level. You can print a message on entry or exit and selectively print input or output values. Adding code to greater statistics will help you understand the behavior of your class. Some operating systems such as Unix, VMS, virtual machine system offers tools to create execution profiles of an application. Typically, tools report the number of times each method was called and the amount of processor time spent in each method. If your system does not have comparable tools, you can instrument your code for gathering statistics, much like for debugging. Then, fifth point, programming in the large. Programming in the large refers writing large complex programs with teams of programmers. Human communication becomes paramount on such projects and requires proper software engineering practices. The following guidelines should be observed. So do not prematurely begin programming. It is important to first complete the generic thought process before comforting the tweak of an implementation target. All software development methodologies emphasize the importance of first designing, then coding. Keep methods understandable. A method is understandable if someone other than creator of the method can understand the code as well as the creator after a time lapse. So keeping methods small and coherent helps to accomplish this. So make methods readable. A meaningful variable names increase the readability. Typing a few extra characteristics is cheaper than misunderstanding that can come later when another programmer tries to decipher your valuable names. Check the reliability of your methods by running them through a spelling checker. Avoid abbreviations that may confuse other programmers. Use temporary variables instead of deeply nested expressions. Do not use two different purposes within a method, even if their uses not does achieve anyway. Use exactly names as in object model. The choice of names used within a procedure additional name for implementation reasons, and this is fine, but the uniformity of names where they carry forward should be preserved. This practice improves the traceability, document and understandability of the software as a whole. Then select names carefully. Make sure your names accurately describe the operations, classes, and attributes they label. Follow a uniform pattern and making up names. For example, you might use the pattern var underscore object is making up operation names such as add underscore element or draw underscore highlight. Be sure to define the verbs being used frequently. For example, you want to distinguish between copy and deep copy or between new and create. So many object oriented languages automatically build method names from the class and the operations. So do not use the same operation name for semantically different operations. All classes all classes that use the same name should have the same origin class and the same signature. For example, number and types of the arguments. So here is one example is given good class and bad class. Suppose there is a class circle, its function is area. This is a good, but this class is matrix and its function is invert. So this is bad because it performs matrix inversion operation. Similarly, class rectangle and we should have to find area. This is a good, but figure and it invert, that is turns figure upside down. So this is the bad class. So use programming guidelines. Project teams should use programming guidelines available in their organizations. If guidelines do not exist, the software team should create guidelines that address issues such as the form of variable names, identification style for control structures, method documentation, headers and inline documentation. Then package into modules. So group classes with similar functions into the modules. Suppose module is plotting, its classes are line plot, bar chart, pie chart. Module is geometry, class is polygon, circle. Class is windows, module is windows, its classes menu, buttons, toggles, panels. Module is animation, classes, scenes, cues, keyframes. So document classes and methods. So documentation of the method describe its purpose, function, contains inputs and outputs, as well as any assumptions and preconditions about the state of the object. You should describe the algorithm, including why it was selected. Internal comments within the method should describe major steps. Publish the specification. The specification is contract between the procedure and the consumer of the class. Once the specification is written, the procedure cannot break the contract. For doing so would affect the consumer. The specification only contains declarations. The user of method should be able to use the method just by looking at specification. Some languages such as Ada and C++ support separation of specification and implementation. Online descriptions of class and its features help promote the correct use of class. Each operation should also documented by itself apart from its method on each class, giving its origin, geometric meaning, telling what each subclass must do to implement the operation and what related methods are needed by the subclass. So this is the example of class description. Suppose here class is a circle. So class description, class name is circle and version of the programming is 1.0. So description, in description, ellipse whose major and minor axes are equal. So we can draw a circle from ellipse. So its superclass is ellipse. So what are the features of ellipse? That is public attributes, center point, that is location of its center. Then radius is real, that is its radius. Then again public methods, draw window, that is draw a circle in window. Then intersect lines, set of points that finds intersection of a line and a circle. It returns a set of 0 to 2 points. Either it may intersect or may not intersect. If there are 0 points, then it may not intersect. If more than 2 points or nearly about 2 points, it intersects. Area of the circle is real. Calculate area of circle. Then perimeter is also real. Calculate circumference of circle. Then private method, there is no private method. So in this class description, its superclass is ellipse and precondition for drawing circle, you should know the major axis and minor axis of ellipse are equal. So it have public attributes, public methods, public attributes, that is center and radius, and public methods such as drawing circle, calculating area, calculating circumference of circle, then intersection of lines, that is set of points, and there is no private method. Then method description. While drawing a circle in class circle, there is intersection line. Intersect line is a method and it is a set of points. What is the description? Given a circle and line finds intersection, returns a set of 0 to 2 intersection points. If line is tangent to the circle, then set of point is single point. You should know this concept. If the line is intersecting it either at one point or 2 points, but line is a tangent, then there is a single point. So what are the inputs for this method? So circle and the line, these are the two inputs. Circle to be intersected with line and line to be intersected with the circle. And what will be returns? A set of intersection points. Set may be 0, 1 or 2. So side effects, no. What may be possible errors? If the figures do not intersect, then return empty set. If the line is tangent to the circle, returns the tangent point. If the circle's radius is 0, then returns a single point if the point is on the line. So you should take these precautions while writing a program. Then third, operation descriptions. So operation descriptions. So operation is intersect line. So origin class is geometric figure and description returns a set of intersection points between the object and the line. The set may contain 0, 1 or more points and each tangent point only appears once. If the line is collinear with the line segment in the figure, only two ends of points of the segment included. What will be the status? Abstract operations in the origin class must be overridden. Inputs geometric figure, figure to be intersected with the line, then line to be intersected with the circle. And what will be the output? The set of intersection points. Set may contains 0 or more points. On what is side effect? There is no side effect. And what will be the possible errors? If the figure do not intersect, return empty set. If the line is collinear with the line segment in the figure, the set included only the end point of the segment, and if the figure is an area, then its boundary is used. This is the operation description. Then next point, object oriented language features. Object oriented languages vary in their support of advanced object oriented concepts. There is no single language that matches all styles and meets all needs. Interpreted languages are useful for rapid prototyping but may not be adequate if you have stringent timing constraints. There is no point in building your own class library if if the language provides one with suitable classes for your design. If you want extra compile time error checking, use a strongly typed language. If memory uses is convoluted in your application, consider languages which provides automatic garbage collection. If you acquire persistent data accessible by multiple users, you may want to consider an object-oriented database unless a language is exceptionally clumsy to use. Syntax should only be minor consideration. So object-oriented language features are multiple inheritance, class library, efficiency, strong typing versus weak typing, memory management, encapsulation, packaging, development environment, metadata, parameterized classes, assertions and constraints, and data persistence. We will study one by one. So first is multiple inheritance. Some languages such as C++, then close FL and DSM support multiple inheritance. Many others do not support multiple inheritance. If the language you select support multiple inheritance, there is a direct translation from your design to implementation. Multiple inheritance introduces the and possibility of conflict among attribute and operation names. A class could have more than one ancestor with the same attribute. There are several approaches that languages take to solving the problem. For example, if a compiler rejects programmers with such classes, then CLOS, on the other hand, has a protocol for resolving them. In any case, we strongly recommended that you avoid such conflicts. Relying on the compiler to resolve conflicts is a matter of poor style because it damages extensibility and can lead to confusion. Then second is class library. Most object-oriented languages include library of useful generic classes which may be used as is or customized to meet a specific needs through the creation of subclasses. The availability of a class library means that many components need not re-implemented by the programmer. The most useful kinds of classes implement general purpose data structures such as assets, dynamic arrays, lists, queues, stacks, dictionaries, trees, and so forth. These classes, often referred to as container classes, serves as framework for organizing collection of other objects. Classes implementing various kinds of associations should also be available in the class library. More complete class libraries might include device independent abstractions of interface classes such as streams, input devices, display devices, file systems, or concurrent processes. A separate library of user interface classes for use with one or more windowing systems is useful. as is a graphic library. Support for string manipulation is needed by most programmers or most programs. So then third is efficiency. Each class has a structure containing methods accessible by objects of the class. A pointer to each method is stored at a known location with the structure. A pointer to method structure for a class is stored in each object. Runtime method resolution is performed by retrieving the method structure and indexing it by known offset of the method. And this technique cannot be used if new methods can be created at runtime or if the name of method can be constructed at runtime because the offset cannot be pre-computed. A language system can further optimize method resolution to use dynamic lookup only where it is needed. A large percentage of the method calls in a typical application can be statistically or statically bound by the compiler if it is provided with enough information. There are two ways the compiler can acquire this information. One way is for the programmer to declare which operations may be overridden, thus limiting dynamic binding to only those functions. Virtual functions of clause and the generic functions of clause reflect this approach. And other approach is to provide final optimization pass that the analyzes the application as a whole, decides what methods are not overridden, and then recompiles the application taking advantage of this information. This approach is adopted by EFL language system. Note that the declaration of types for variable allows the compiler to be much more precise in its determination of which method calls can be optimized. Then fourth is strong typing versus weak typing. Object-oriented languages vary greatly in their approach to typing. In terms refer to whether each variable and attribute value is merely known to be an object, that is weak typing, or may be declared more precisely belonging to a particular class or part of its descendants, that is a strong typing. For example, the attribute radius is declared by type length. Smalltalk is weakly typed language. All variables in Smalltalk are objects of unspecified class. EFL, DMS, Objective-C, and C++ are strongly typed languages, whereas a Smalltalk is weakly typed language. Clause and Objective-C support strong typing but do not require its use. A variable an that references an object may optionally be declared, and the compiler will check uses of that variable. Hybrid languages such as DSM, C++, and Objective-C even permit an attribute to assume a value which is not the object but rather the underlying C language type. Permitting non-object values increases efficiency of common operations such as arithmetic at the some cost in uniformity of references. Then strong typing in language serves two purposes. Strong typing provides active support to the programmer in detecting mismatched method arguments and assignment statements. Strong typing also increases opportunities for optimization. The compiler can detect when a general purpose operation can be replaced by specific function call. No power is lost by use of strong typing. The programmer can always declare everything to be a class object to get the same effect as weak typing. Although weak typing is flexible and powerful, it permits dangerous coding practices. Modern programming languages theory has been evolving in the direction of strong type checking. Much of the advances in programming languages theory have derived from restricting the programmer's ability to perform dangerous operation. Most new languages support strong typing. The premise behind strong typing is that it is easier to detect and correct software bugs at compiler time rather than at runtime. Strong typing improves the reliability of delivered software. Then fifth is memory management. The freedom with which object can be created and accessed causes a problem when memory space must be reclaimed. Most object-oriented languages allocate memory from the heap rather than using fixed blocks of global memory or a stack. A dynamic memory allocation system can run out of memory unless the objects that are no longer needed are deallocated. The principal problem lies in determining when an object is not needed or can no longer be accessed. The, se- the severity of the problem depends on the type of application and the memory architecture. Many programs that have access to a large amount of virtual memory can simply ignore the problem. On the other hand, a highly interactive application expected to run indefinitely must consider memory management no matter how large the available memory space. So there are two approaches to memory management. Either it is done automatically by runtime system of the language or it is done explicitly by deallocation statement written by the programmer. The preferred approach, automatic memory management, relieves the programmer of responsibility of deciding when to deallocate memory and avoids risk of dangling object references that explicit deallocation is important too. However, users are understandably dissatisfied with some garbage collection schemes that result in long pauses at unpredictable points during execution. Incremental garbage collection schemes avoid long delays but impose a higher average cost. Improved garbage collection algorithms offer some hope in this area. Then Close and Smalltalk offers fully automatic garbage collection. C++ requires the programmer to deallocate unneeded objects, but C++ language allows the programmer to define destructor functions, which are called automatically when a variable goes out of scope. This gives a programmer a convenient way of organizing and invoking explicit storage deallocation, but is not a garbage collector. Dynamically allocated objects must be explicitly deallocated by delete operator. Explicit deallocation runs in dual risk of deallocating objects that are still referenced, that is leading to program crashes, and failing to deallocate objects that are inaccessible, that is leading to memory wastage, but it does not impose the any additional time or memory cost on the program. Then sixth is encapsulation. Encapsulation, also known as information hiding, which consists of separating the protocol, the external aspects of the object that are accessible to other objects, from the internal implementation details of the object which are hidden from the other objects. Encapsulation prevents a program from becoming so interlaced that a small change has massive ripple effect. You can change the implementation of the class without affecting its clients. You may want to change the implementation of an object in order to improve performance, fix a bug, consolidate code, or port it to a different system. Encapsulation is not unique to object-oriented language, but the ability to combine data structure and behavior in a single entity makes encapsulation cleaner and more powerful than conventional languages that separate the data structure and behavior. Languages differ greatly in the degree which to the class boundary is enforced. So one way that encapsulation can be violated occurs when code associated with one class directly access the attributes of another class. Direct access makes assumptions about the storage format and the location of the data. These implementation details should be hidden within a class. For example, an attribute value may actually be computed from other information. The proper way to access an attribute of another object to ask for it by invoking an operation of the object rather than simply taking it. Many languages, such as a Smalltalk, forbid direct access to the attribute of the another object, or as in C++ and Thales, all permit attributes to be declared either public or private. FL provides perhaps the finest control of the encapsulation through its export statement, which lists attributes that may be read and operations may be executed. The C++ friend declaration allows limited loosening of encapsulation for access by specified classes or functions. So encapsulation can be violated through the careless use of inheritance. A subclass inherits the attributes of its superclass, but if the methods of the subclass directly access superclass attributes, the encapsulation of the superclass is defeated. The clause all FL and C++ permit a class to restrict its visibility from its subclass. There are arguments in favor of allowing a class to access its superclass, but the cost of tight binding between the classes. Often it is useful to write some private operations that are for internal use only by other methods of the same class. It is desirable to restrict the visibility of these operations such that the other classes cannot use them. It is often necessary to allow subclasses to access these internal operations. So simple distinction between public and private is not possible. Some languages permit a third level access to subclasses known as protected declaration. Then seventh is packaging. The class is not adequate structuring constructs for a large systems. Most object-oriented languages lack partitioning mechanisms for the controlling visibility between the classes. We have suggested the use of modules containing classes as a structuring mechanism during analysis. A related problem is that object-oriented languages typically require that the names of the classes must be unique. Often, this is not a case when two or more applications that were developed independently are combined. For example, two designers working independently might define different versions of a class called a symbol with different operations and semantics. The problem is similar to names classes in block structured languages. फक्त 5 राहिलेत तेवढे पूर्ण करतो आणि थांबूया. Then in Ada language and close, repackage constructs provides the means to structure a system into separate components with their own namespaces. In ADA, names declared in the specification of package are not visible outside the package unless explicitly requested, allowing the control of both the namespace and interpackage dependencies. Entities that are known by the name outside the package can be renamed within. Packages may be nested, allowing the entire subsystem to be encapsulated within a well-defined interface. Object-oriented languages would benefit by the addition of packaging capability. In particular, the ability to nest the packaging components of the system allows better control of visibility. Then at development environment, the tools that are available for browsing and editing source code, compilation, debugging, system integration, and testing have a big effect on your productivity. Support tools are especially important in object-oriented languages because of difficulty of managing inherited and dynamically bound features in a large system. A browser allows you to explore the source code in structured way, asking what classes are present and what operations are defined for each class. The compiler or interpreter is the most important implementation tool. Whether the language is interpreted, compiled, or translated affects the speed with which you can make small changes and test their effect. An interpreter allows more flexible debugging. Inter- Interpreted systems such as Smalltalk and Lisp allows an executable program to be stopped, edited to correct a bug, and resumed. Objective-C offers an optional interpreter in addition to the compiler. Some compilers translate an object-oriented language to an intermediate language such as C, which is then compiled. The C++ language was the first implemented by translation into C, but true compilers are now available. Translation may pose problems for symbolic debuggers because they do not understand the original object-oriented code. In evaluating the debugger, find out whether it shows you the original object-oriented source code or to intermediate code, which may be hard to read. The debugger should be able to inspect attribute values and evaluate object-oriented expressions. Tools for system binding and change control are essential for large projects but are also valuable for individual programmers. Consider whether the proposed language provides them to integrate smoothly with existing tools. System rebuilding rebuilding can consume much time if A simple change in one module require that client module must be recompiled as well. Try to determine what kinds of change trigger recompilation of the clients. Experience has shown that the use of conventional building tools such as Unix make it is too crude for many purposes. Finer grained development environment are needed but are only recently available. Then ninth is metadata, which is data about data. Metadata that is present at a runtime allows metadata is data about data which is present at runtime allows an application to reason about and possibly even change its own structure and capabilities, including the operations and object support, the attributes it possesses, or the types of attributes. There are also more conventional uses of metadata, such as writing a generic procedure that print or save any object using the attribute names and the types. Languages containing explicit class descriptor objects such as a Smalltalk and DSM, which contains runtime metadata about the classes. For the creation of a class object act as a template for the creation of new instances. The class may also contain description of the attributes and the operations such as name, type, or arguments. For example, a complex number class might define a real part and imaginary part attributes, and each of which is presented by 32-bit floating point number. Of course, the designer of the system knows metadata. So, in principle, these data could be embedded in the code. But if the design changes, then all code that depends on embedded data will be become invalid. The use of metadata at runtime rather than the compile time allows the construction of extensible systems with generic procedures and abstract classes that are reusable in foreseen in
बस की
unforeseen
सर.
applications. Metadata also can be used to support data persistence or by programming support tools such as debuggers, browsers, and inspectors. Then 10th is parameterized classes. Parameterized classes are generic, allow a parameterized template to be written that that can then be applied in several cases that differ only the types of the parameters. For example, generic list class can be instantiated as list of points or list of integers. The generic add element method on the list implicitly depends on the type of element. So local variables within the method have generic type that depends on the instance. Parameterized classes are present in Ada language and in FL. Parameterized template have been proposed in C++. Then 11th point is assertions and constraints. So assertions and constraints improve the odds that the behavior of the class matches and expectations of its clients. We can do this informally by writing a natural language description of desired behavior. But how can we be sure that the description will be understood in the same way by another program who wants to use the class? Usually, there are a few critical assumptions about the behavior of the class, operations, or method that can be expressed mathematically. These assumptions take the form of assertions that must be true at particular points during executions, such as preconditions and postconditions, and constraints that must be maintained on invariants that must always be true. Assertions should also be written into the software in a form that can be optionally compiled and automatically checked at runtime. While this technique can be used in many languages, such as assert macro available in C implementations, it is particularly well supported in EFL language. So constraints can be more than simply conditions to be tested. They can be viewed as the way of expressing declaratively what might otherwise have to be written in procedural code. A language system could understand constraints that are declared and ensure that they remain true by taking action at runtime to maintain the constraints. The Prolog logic programming language has such capabilities. It would not be surprising to see such constraint maintenance systems become widely available under object-oriented languages. And last point, all the computer that is data persistence, all the computer programs operate on data. If you require data that persists beyond the lifetime of a single program execution, then you will need to use permanent data store. There are various reasons for waiting for wanting persistence data. What are the different reasons? The persistent data may provide the easiest mechanism for passing data from one program to another program. Persistence data allows the same program to resume processing at a later date. Data store are often useful for historical or archival purposes. There are several approaches to provide persistent data services, files, special purpose hardware devices, databases, and intrinsic language support. Some new object oriented databases are especially convenient in their data storage services. To a large extent, such an advanced object-oriented database looks like an object-oriented language, except that the orthogonal property of persistence may be specified for data structures. The advantages and disadvantages of the object oriented databases relative to conventional databases. So these are the points of object oriented styles. Next point, object oriented compiler and object diagram compiler and object diagram animation we will cover in next lecture.